Hi, everyone. It is a pleasure to chat with you today. I will talk to you a little bit about some of the things that I'm interested in my research. So with that, we will talk about the melting of ice, a Brazilian favorite dish. I am Brazilian, and how that all connects to partial differential equations, which is the field that I work on most of the time. So let's get started. So first of all, let me describe where my research, the area that I mostly work on, where it lies within mathematics. So I would say that partial differential equations is in the planes of analysis. If you see here, this is not a picture that I did, by the way. This is from the internet. And that has a lot of connections, and we will see some of them today with complex analysis, with probability. So you see there the probabilistan area. And then it also has connections to the hills of differential geometry and geometry itself. And then, there are people who work in analysis and also have connections to other things. So let us see, in my case, how this connects with other things. So I will start with a motivation for why we work on these types of problems, and that is going to be one of the most beautiful equations of all time, I should say, the heat equation. So our goal is going to be to describe the diffusion of heat. So let's say we have an infinite metal sheet. Let's say we have R2, and I should say, I know that oftentimes when we are modeling things coming from physics, we make this kind of absurd assumptions, but bear with me for a second. This is just going to give us a motivation for a problem we can actually work with for now. So let's call U of x, y, t the temperature. So at a point x, y at time t. And our goal would be to understand what is the temperature at any given point at any given time. So we have to, of course, life is not free. We have to know something to begin. So let's say that we know the value of the temperature at time 0 for every point xy. So this is U of xy 0. Then we use physical laws. So in this particular case, we use the beautiful Newton's law of cooling, and we obtain an equation that describes how the temperature changes with time. So there are some constants that pop up here. So there is the sigma over kappa, and then you have the partial derivative of u with respect to time, and that is equal to the sum of this second, let's say, pure partial derivative, so del 2u del x2 plus del 2u del y2. And here, sigma is a positive constant, which is the specific heat of the material, and kappa is the conductivity of the material. So if you are super interested in this, you can take a look at this a little bit more or chat with me later. But let's not worry about this too much. We can even pretend that sigma over kappa is 1 for our purposes for now, so we don't worry about it. So Laplace's equation will come from this. So we look at this equation that we got by using Newton's second law, and after a very long time, very, very long time, there is going to be an equilibrium. So there won't be any heat transfer anymore. And with that, we attain an equilibrium. If there is no heat transfer anymore, the temperature doesn't change with time. So in the long run, right, after a very long time, we think that del u del t is 0. And if that is the case, then our equation becomes the Laplacian, which is this beautiful triangle of u. So, and that is the sum of the second partial derivatives with respect to x and y. And that should be 0 because that is del u del t after a very, very long time. And that is Laplace's equation, which is absolutely beautiful. And we'll talk about this some more. It has connections to a lot of very beautiful math. So here the triangle is the Laplacian operator, and we'll talk about it. Let me just say a little bit of history here. There's a lot more to be said, but the equation Laplacian of u equals 0 showed up probably for the first time in an article by Euler, who was alive between 1707 and 1783, about hydrodynamics. Euler was a Swiss, I should say, mathematician, physicist, logician, engineer. He was a fantastic scientist working on many different things. And he made very important contributions in calculus, graph theory, topology, number theory. You see that back in the day, people were working in a lot more fields than probably nowadays is the case. Euler also introduced notations and definitions that we use in modern mathematics nowadays. So super important. But the equation is actually called Laplace's equation, right? So why is that? This is in homage to Pierre-Simon Laplace, who was a French mathematician, and he studied this equation while he was investigating the gravitational attraction of bodies in space that has really important applications. So Laplace was also working in many different things, and he made very, very important contributions in engineering, math, stats, physics, astronomy, and philosophy. And I'm sorry for my dog walking back in the back. You might know the Fourier transform, which is so important for so many things. This was introduced in big part by Laplace. And I should say that the Bayesian interpretation of probability was also developed mainly by him. So lots of super important contributions. Let's talk about the Laplacian and physics a little bit more. So the Laplacian shows up in a lot of different problems in math physics. It shows up in the study of electrostatic fields. It models the potential energy of a particle being acted on by gravitational forces, which is how this showed up first. It also models the flow of fluids, and as we saw, it models the stationary state of temperature. It appears in wave propagation, in quantum mechanics. Seriously, the Laplacian shows up everywhere. It is probably the most beautiful operator there is. So let's talk about functions that solve Laplace's equation. So I will say, oh, sorry for this. A function, let's say of class C2, so it has second partial derivatives and they are continuous. This is a solution of Laplace's equation, which is the sum of the second partial equal to 0. So that's just the definition, okay? This is called a harmonic function. And I would like to talk about harmonic functions for a little bit. So first of all, harmonic functions are absolutely awesome. So they satisfy a lot of truly magical properties, I should say. So let me start with one that I teach in complex analysis when I teach complex analysis. So let's say we have a function that is harmonic, and that just means it's a function of x and y. And if you sum the second partials with respect to x and the second partials with respect to y, you get 0. And let's say that that is true in the unit ball, okay? So in R2. And let's say that you have a point x inside of the unit ball. And then if you look at this little ball closed, so I'm including the boundary, of radius r that is fully inside of B1. So I'm talking about this blue ball right here, okay? So if this ball is fully inside of the ball of radius 1, then if you integrate the function u, which is harmonic, over this ball, and you divide by the volume of the ball, so this is an average, what you get back is the value of the function u at the center x, which is pretty insane, actually. It's a magical property of harmonic functions. You can also do this if you are integrating over spheres as opposed to balls. So if you integrate over the boundary of the ball, which is the sphere, and then instead of dividing by the volume, you divide by the area of the sphere, you again recover the value of the function, the harmonic function u, at the center, which is super amazing. A third property, which is absolutely super awesome, is that if a function solves Laplace's equation, notice that to write Laplace's equation, there are ways to think about functions that have weak derivatives. I'm not going to get into this, but let's say that we are very conservative and we start saying, okay, to be harmonic, a function has to have second partial derivatives. Let's say they are continuous. So we start assuming the function is of class C2. Then actually, because it solves Laplace's equation, you can prove that it is actually a function of class C infinity, which is super incredible. Some more incredible properties of these amazing harmonic functions. Let's say, first of all, we have a function that is harmonic in an open bounded set, and let's say that u is harmonic there, and it is continuous all the way up to the boundary. Then we have something that in partial differential equations is extremely useful, and that is the maximum principle. So for those of you that have seen some topology, if we have a continuous function on a compact set, and the compact set here is the closure of u, then the function will attain a maximum and a minimum. And what the maximum principle is telling us is that the maximum of the function over the compact set, which is the closure of u, of capital U, the domain, right? Actually has to be the same as the maximum of the function u restricted to the boundary of the domain. And the same is true for the minimum. That's pretty incredible. So if you look at the value of the function just on the boundary, and you look at what the maximum is, that is going to be the maximum of the function over the whole closure of the domain. Same for the minimum. And then we also have the strong maximum principle, which is also a theorem that is extremely important in partial differential equations. So if we say that our domain capital U is connected, and let's say that there is a point inside in which the function attains its maximum value, because notice that the first maximum principle we discussed didn't rule out the fact that maybe there is also a point inside where the function attains the maximum. It's just saying that there is a point on the boundary in which that's true. The second, the strong maximum principle, is saying if the domain is connected and there is a point inside in which the function attains the maximum value over the whole compact set, the closure of capital U, then actually the function has to be constant. And the same is true if there is a point inside of the domain in which the function attains its minimum value. So super interesting, and that is a consequence of the function being harmonic. Now, I told you that I teach these things when I teach complex analysis. So let us talk about the connection of these beautiful harmonic functions to complex analysis. So first of all, let me give you one way of defining a complex derivative. So let's say that we have a function f defining a domain of the complex plane. So this is the xy plane in which we are defining how to multiply vectors in a specific way. We have the complex numbers. So a function will have complex derivatives, a complex derivative at a point, let's say z naught, if the limit that we think of when we think about the derivative of a function of one variable, but now we are thinking about this as a function that is a function of complex numbers, which means that it makes sense to divide by z minus z naught, okay? These are complex numbers. If this limit exists, we say that the function has a complex derivative at z naught. And then let's say if I have a function on the whole complex plane, taking values in the complex plane, this function is going to be holomorphic. We also say entire in this particular case, if the domain is the whole complex plane, if it has complex derivatives at all points in the complex plane. And now what's the connection between these functions that are analytic, that's also another name that we use, and these harmonic functions? So if I have a function that is holomorphic or entire, and this function is equal to, let's say we write it as a real plus I, an imaginary part, so u plus iv, then both u and v are actually harmonic functions, which is pretty incredible. So you can prove a lot of things about analytic functions or these functions that are holomorphic using theory from harmonic functions and vice versa. I should say that depending on the domain you're at, so here I wanted to simplify things, so I have functions defining the whole complex plane. If you are defined in some specific types of domains inside of the complex plane, then you can do a reverse. If you give me a harmonic function, then I can create an analytic function whose real part, for example, is the harmonic function we started with. But then we have to put a little bit some conditions on the domain. So let's not worry about this. So having discussed the Laplacian, I would like to talk about one of the most important problems in partial differential equations. So that is a boundary value problem. And I'll talk about the Dirichlet problem for the Laplacian. So we are going to be given a domain omega in Rn. If you like R2, think of R2. I'm going to be given a function phi. This is going to be my boundary data. So phi is going to be a continuous function on the boundary of the domain. I'm going to have some function f, which is going to be like the right-hand side of my equation, let's say continuous. And I would like to find a function that is of class C2, which is continuous all the way to the boundary, so that the Laplacian of u is equal to f inside and u is equal to phi on the boundary. Remember, I want u to be continuous all the way to the boundary, right? So this is the Dirichlet problem for the Laplacian. Now, it's super interesting that you can see this problem, which is a PDE problem, a partial differential equation problem, as a minimization problem. And this is something that can be done for a lot of different problems. So solving this is the same as minimizing what we call an energy. So here we have J of V, which is an integral of, this is the gradient of V squared plus 2f, which is the right-hand side, time v. So if you look at the value of this energy for all functions that are equal to phi on the boundary, and you take the minimum, that is going to give you a function that is actually a solution of the PDE problem that we started with. So instead of working with the PDE, you might be actually looking at minimizers of this energy instead. So let's see an example in R just to simplify our lives and so we can see. So let's say also that f is 0, so I just have the gradient squared, which in this case is the integral, let's say from 0 to 1, that's the domain, of v prime squared. And I would like to minimize this energy among all functions, and now I'm going to give you some boundary data that I created. So let's say at 0, we are -1, and at 4, we are equal to 3, okay? So that's actually pretty interesting. And so these are the boundary data. And then you will see that actually the minimizer you can actually compute by hand. The minimizer is going to be a straight line, and it's going to be the line x minus 1. And this is a function that is harmonic, because if you take the second derivative, it is 0, okay? So that is beautiful. So that is awesome. It's a simple example we can compute by hand. I would like to make this a little bit more interesting. So I'm now going to add an extra condition, okay? So not only do I want to minimize this energy among all functions that satisfy my boundary data, but I have an extra condition. And the condition is I have to stay on top of what we call an obstacle. So in this case, I drew the obstacle as this parabola, that's the red curve. And I'm saying that I have to stay on top of this obstacle always. So you can also compute this by hand. It's a little bit more work, but you can do it. And you will see that the function you get that minimizes your energy is actually a straight line. If you see this from 0 to a little bit right there. And then there will be a point in which you hit the obstacle, if you are the straight line. But then you have to be greater or equal than the obstacle. So you're going to follow the obstacle. And then there is a moment in which you can be the line again and still be on top of the obstacle. So there's going to be some interesting regions there. There will be regions in which you're still the line, which means that you're still harmonic. And then there is a region in which you are equal to the obstacle. So this is an example of the classical obstacle problem, which is a prototypical type of a free boundary problem. So let me tell you about this a little bit. So let's say we want to minimize the energy we were describing before, the little bit more general one in which you have the gradient squared plus 2fu. And you want to do that among all functions which are equal to phi on the boundary. And then let's say that inside the obstacle is 0, okay? So you have to be greater or equal to 0 inside of your domain. This is a free boundary problem. And let me explain why we call it this way. Solving this problem means you not only have to find the function u, but you also have to find the region in which it solves the PDE being Laplacian of u equals f, which means that you are interested in understanding what is the boundary of the region in which the function solves the PDE, which is what we call the free boundary. In this case, it's the boundary of the region in which u is greater than 0, because here 0 is the obstacle. So in this particular case, let's see what's happening. There is a region in which you are above the obstacle. Let me go back a slide for a second. So here, in the region in which we were above the obstacle, that's exactly the region in which we were a straight line, in which case we were harmonic. So here, in the region in which we are above the obstacle, which is 0, we are going to solve the PDE. So the Laplacian of u is equal to f. And then there will be a region in which we are equal to the obstacle. In the previous example, that would be the region in which we're coinciding with this parabola. And in that case, we're going to be equal to the obstacle, which in this case is 0. And then the free boundary is the boundary of this region. So solving the PDE means we have to find a function, but also the region in which the function is solving the PDE. So we're interested in the free boundary as well. So you can also rewrite this problem using a PDE, and you end up showing that the Laplacian of u is not just f, right? Because it's not f always. Sometimes the Laplacian of u is 0. So the Laplacian of u will be equal to f times this function that we call a characteristic function. So this is a function that is 1 if u is greater than 0, and it is 0 if u is not greater than 0. Okay, so whenever u is greater than 0, the Laplacian is f, and whenever u is not greater than 0, which means in this case it's 0, then the Laplacian will be 0. And we also have the condition that we are always greater or equal to the obstacle, so u is greater or equal to 0 if the obstacle is 0. So this is an example of a free boundary problem. So why do we work with these free boundary problems? So in many problems from the applied sciences, the situation is delicate. The domain where the function solves a PDE is not known a priori. Only a portion of the boundary is prescribed. In the remaining part of the boundary, which we don't know a priori what it is, that's the free boundary, we impose additional conditions to be able to solve the problem. Okay. So let me give you some other examples besides the classical obstacle problem, which is the one we just saw. We have the no sign obstacle problem, in which the Laplacian is equal to the characteristic function of the set where, so here omega is the unit ball, take away the set where both u and its gradient are 0. So notice here that the Laplacian will be equal to something that depends on the solution u as well. That's the point. We also have the superconductivity problem, where the Laplacian of u is equal to another characteristic function of a set that depends on u. So here omega is the set where the gradient is not 0. We have the two-phase membrane problem, where the function can be positive or negative. So now the Laplacian will be some weight lambda plus, where u is positive, minus some weight lambda minus, where the function is negative. So all of those are examples of free boundary problems. So I told you we were going to talk about the melting of ice, and here we are. This is also called the Stefan's problem. And this describes the temperature distribution in a homogeneous medium going through a phase transition, such as ice becoming water, the melting of ice. So the model we have is we want to solve our old friend, the heat equation. We're going to impose a condition in the boundary between the two phases, the water and ice. And this boundary is an unknown surface that we call the free boundary. So we have T1, the water temperature, T2, the ice temperature, and then we have the heat equation in the water phase, the heat equation in the ice phase. At the interface, the two temperatures are the same, and then there is an extra condition that we impose in the interface ice-water that is there with the normal derivatives. So this is connected to the speed of the interface ice-water in the direction of the normal. So there is an extra condition we have to impose on this free boundary. So let me tell you a little bit about the history of the obstacle problem, which is one of the most famous free boundary problems. The study of this beautiful problem began in the 60s with the work of Stampacchia, Levy, and Lyons. Let me tell you a little bit about these incredible people. And during the last decades, I should say that this has led to really beautiful developments in the calculus of variations and PDEs. And I, among a lot of other people, have been working with these types of problems. So let me start with Guido Stampacchia, who was an Italian mathematician known for his work in calculus of variations and elliptic PDEs. So he did incredible contributions in the theory of free boundaries. Hans Levy was a German-American mathematician known for his work in PDEs and complex analysis of several variables. So thinking back at what we talked about, the complex analysis, so this goes a little bit further with several variables. And then Jacques-Louis Lyon was a French mathematician who did a lot of incredible things for PDEs, stochastic control, and other areas. Maybe I can mention that he received the Science John von Neumann Lecture Prize in '86, among many other distinctions. So an incredible mathematician as well. And let me tell you how the theory of free boundaries kind of came about. So the study initiated by Stampacchia, Levy, and Lyons opened the doors to a lot of developments, and one of them was the study of free boundary problems. And I should say a big name that we definitely have to mention when we talk about free boundary problems is Luis Caffarelli. So Luis is an Argentinian mathematician who he recently retired at the University of Texas at Austin, and he is incredibly famous in our community. He wrote a lot of groundbreaking papers One of them is called The Regularity of Free Boundaries in Higher Dimensions, which was published at ACTA, for example. He received a lot of awards, including the Wolf Prize in 2012 and the Shaw Prize in 2018, and he has truly done an insane amount of groundbreaking work. So it is impossible not to mention Caffarelli basically all the time when we talk about free boundary problems. The study of free boundary problems continues to be super active. There's a lot of open problems that are attracting mathematicians from all over the world. It also has a lot of connections to geometric measure theory, the study of minimal surfaces. So there are other, let's say, communities of mathematics that relate to free boundaries quite deeply, and the mathematicians interact and get ideas from each other. So let us go back to the classical obstacle problem in a context that is very dear to me, and that is a picanha problem. So picanha is maybe one of the most famous Brazilian dishes. We love meat, and that is a special type of cut we do. So a lot of our barbecues involve picanha. So let's talk about a picanha problem. So let's describe the classical obstacle problem through food. So after a barbecue, let's say we have some leftover. Well, usually that's not the case, but let's say we do, and we want to wrap some dish of picanha, like the one in the picture, in a plastic wrap so it doesn't dry out, so you can eat it tomorrow. Here, the food is the obstacle, and the configuration of this plastic wrap, after it adjusts to the geometry of the food, represents the solution to the classical obstacle problem. Another way to see this, perhaps a little bit more serious, is let's say we have a membrane over a plate. So the plate is fixed, you have a wire, and then attached to this wire, you have a membrane, and the membrane has to stay on top of the plate. So here, notice that there is a region in which the membrane is touching the plate. That is what we call the coincidence set. And then there is a region in which you are above the coincidence set. So the plate is playing the role of the obstacle in this case. And then the fact that you have to be attached to the wire is giving you your boundary data. So mathematically, we are given a function phi, let's say of class C2 on the domain, which is our obstacle. So we will have to stay on top of the obstacle in the domain. I have some boundary data psi. So the obstacle, let's say, is less than or equal than psi in the boundary. These are the boundary values. I'm going to have, once again, something playing the role of the right-hand side, let's say f. I'm not going to require much of it if you have seen what it means to be L infinity, let's say bounded in some sense. And I would like to minimize an energy. So this is the gradient squared plus 2FU, like before. And I'm going to minimize this energy, which is motivated from, remember, this minimization comes from a PDE. And I want to minimize it over the set of all functions that are equal to psi on the boundary of the domain. Remember the membrane, right? On the boundary, you have to be attached, so you have boundary data, and you are greater or equal than your obstacle almost everywhere in your domain. So another picture you can keep in mind is like this mountain. So you have some boundary data. On the boundary, you have to be attached to something, so you're prescribed. And then inside, you have to stay on top of your mountain. So notice here that there is a region in which you are equal to the obstacle. That's going to be where you're equal to the mountain. That's the coincidence set. And then you detach. And that's going to be the region in which you're going to solve your PDE, okay? And the boundary of the region where you're equal to the obstacle is going to be what we call our free boundary. So here in 2D, a little bit easier for us to see. So once again, let's say that we have the domain between 0 and 4. Let's say that the obstacle is this red parabola. And we have prescribed boundary data. So at 0, we are -1. At 4, we are 3. And then we also have to stay on top of the obstacle, like before. So notice here that there is a region in which you are detached from the obstacle, where you are the straight line. And in that region, you are harmonic. Then there is the boundary of that set. This is gamma. These are in these 2 points. This is the free boundary in this particular case. In higher dimensions, the free boundary is way more complicated. Then you have the region in which you're equal to the obstacle. And then in this case, you have the second free boundary point, and then you detach again, and you are harmonic. So if you think about this, you are able to prove in higher dimensions as well that there exists a unique minimizer, and this minimizer will satisfy the following equations. Its Laplacian will be equal to the right-hand side f when you are detached from the obstacle, and when you are equal to the obstacle, then the Laplacian of the minimizer will be equal to the Laplacian of the obstacle. If the obstacle is 0, of course, that means you would have a harmonic function. okay, in that region. The coincidence set is the set in which the minimizer is equal to the obstacle, and the boundary of that set is what we call the free boundary. So the first fundamental question we're interested in is how regular or how smooth is the solution U? And I should say, folks, that there is a way for us to work with Sobolev spaces, so we don't actually have to require that the function has a lot of derivatives to begin with. But then, of course, you want to prove that this minimizer, which lives in a Sobolev space, for those of you that have heard these words, which means I'm not requiring actual derivatives in the traditional sense, if they actually have traditional derivatives. And in this case, you can prove that, yes, the function has to have first derivatives, and those are Lipschitz. So the function is actually C11 log, and that is the optimal regularity for this specific problem. And then the second fundamental question is, what about the free boundary? What can we say about the geometry of this set, which is how smooth is this free boundary? So in 77, Kinderler and Nirenberg proved that if we know that the free boundary is C1, and I should say that that means that locally it's the graph of a C1 function, then actually it's C infinity, which means it's the graph of a C infinity function. Around that time, Luis Caffarelli, developed his theory of the regularity of free boundaries. And he proved, I'm being very careless here, not getting into a lot of technical details. So he proved actually how to go from flat. If your free boundary is flat, it has to be the graph of a Lipschitz function. And if it is Lipschitz, it has to be actually the graph of a C1 alpha function. So that means that you can go from being flat to being C infinity. So if you're flat, you have to be C infinity, which is pretty incredible. So just to clarify here, talking about the regularity, the Lipschitz, that word that I mentioned before. So a function is Lipschitz, which is denoted by C01. If when you compare the value of the function at x with the value of the function at y, so not only the function is continuous, but there is a rate of decay. So if x and y are close enough, then f of x and f of y are close enough by a factor c. So that's your Lipschitz continuity. If instead of having on the right-hand side x minus y, you have x minus y to the alpha, you have what we call Holder continuity. So let me give you a few examples. X is Lipschitz, x to the alpha is C alpha, Holder with exponent alpha, and x to the alpha plus 1, that is a function that has first derivatives, and the first derivatives are Holder with exponent alpha, and we denote that with C1 alpha, okay? So just to have some examples of regularity to understand what I'm referring to. So now let's push this classical obstacle problem a little bit to a slightly different problem. So this is like a wall problem. So instead of having an obstacle that is defined in your whole domain, you're going to have an obstacle that is defined only on a portion of your boundary. So on the rest, you're going to be prescribed. And then in a portion of the boundary, you will be restricted to being above an obstacle. So this is like, okay, you have to stay on top of a wall. So we are given a domain. Let's think about this domain as being the upper half ball, okay? So we have here the upper half ball. And I'm going to have a codimension one manifold. If those words are scary, don't worry about it. In this case, let's think about it as the flat portion of my domain. And on this portion, I'm going to have a function phi, which is defined. And over here, I have that u has to be greater or equal to phi. And on the curved part of my boundary, I have prescribed boundary data. I have to be equal to psi. And let's say I want to minimize the gradient squared over all functions that are equal to psi on the curved portion of the domain and on the flat portion that are greater or equal to the obstacle. So this is called the thin obstacle problem because the obstacle now lives in a codimension one manifold. So this problem is also called a Signorini problem, and that is because it was first described by the mathematician from Italy, Antonio Signorini. He presented this problem during a course he was teaching in 59. He called it a problem with ambiguous boundary conditions. And the reason for that is at every point on the flat portion, you're going to have to satisfy one of two conditions, but in principle, you don't know which one of the two you have to satisfy, okay? Fischera, a student in this course, started working on the question of existence and uniqueness of minimizers when Signorini got very sick. In 63, Fischera found a proof of the existence and uniqueness and presented a note to Signorini apparently exactly a week before he died. He was super happy, and the story goes that he told his doctor, "My student Fischera gave me a great joy." And then the doctor said, "But you had many joys in your life, professor." And he said, "But this was the biggest of them all." And the story goes that those were his last words. So where does this obstacle problem show up? So it was modeled by Signorini in the context of elasticity. So if you have an elastic body at rest, partially laying on a surface M, it also models the flow of a saline concentration going through a semi-permeable membrane when the flow has a specific direction. So this is in the context of osmosis, or the parabolic version of the Signorini problem. It also has applications in math finance when we're talking about American options. So, and there are variations of this that model a lot of different things, including combustion and other things, if you change your operator to the fractional Laplacian, for example. So this problem has a lot of applications. Let's talk about it a little bit, and for that, let's fix some notation. So once again, let's say that our domain is the upper half unit ball. So this is going to be called D, so that this is B1 plus to say it's the upper half. And the manifold, the thin codimension 1 manifold, is going to be the hyperplane xn equals 0 intersected with the unit ball. So you have what we call a thin ball, and that is denoted by B1 prime. So we have a couple of definitions. We have the coincidence set, which now lives in a codimension 1 manifold. So that is the set in this thin ball where U is equal to phi. And then if you look at the boundary of that set in the relative topology of Rn minus 1, then you get the free boundary. So you're interested in the geometry of the free boundary and the regularity of a minimizer U. So first of all, working with these half balls is kind of inconvenient. So we extend our minimizer evenly. We extend the boundary data evenly to the unit sphere. And if we do that, this extension is the unique minimizer of the Dirichlet energy, the integral over the unit ball of the gradient squared, over all of the functions that are equal to psi, my boundary data, in the unit sphere. That's what I'm denoting with S1. Which are greater or equal to phi in this thin ball, okay, our hemisphere here. So the properties of our minimizer are going to be what we call the Signorini conditions. So first of all, we're going to have a harmonic function, but not a cross. So we're going to have a harmonic function in the upper and lower half balls. And then if we want to understand what happens in the thin ball here, where things go wrong, you are going to be greater or equal than the obstacle that's given because you're taking a minimizer among functions that satisfy that. Then you're going to have a condition on your normal derivative right here. And then there is this very interesting dichotomy condition, which says that either you are equal to the obstacle in the thin set, or the normal derivative has to be 0. So one of the two, okay? These are the ambiguous boundary conditions that Signorini was referring to. With respect to the regularity of the solution, this is different from the classical obstacle problem. So the best we can hope for the Signorini problem is C1 1/2. So that means I would expect the function the best possible to have first derivatives, and the first derivatives are Holder with exponent 1/2. But notice that this is not a cross, okay? So this is in the upper half ball all the way to the manifold, and in the lower half ball all the way to the manifold, but not a cross. And the reason for that is we have an explicit solution of the Signorini problem when the obstacle is 0, and that is the real part of x1 plus ixn to the 3/2, and that has exactly C1 1/2 regularity, and not better. So, of course, this begs the question, can we prove that for any obstacle, not just 0, the function has C1 1/2 regularity? And let's talk about a little bit of history. So Athanasopoulos and once again Caffarelli in 2004, in a groundbreaking result, they were able to prove that, yes, you do have C1 1/2 regularity. This was proven following a result of Richardson that had proven this, but only in dimension 2. And Richardson used complex analysis methods, see how these things are connected, But unfortunately, these methods could not be generalized for higher dimensions. So Athanasopoulos and Caffarelli really needed new ideas to be able to prove that result in higher dimensions. And then I should mention that actually on my PhD thesis, I generalized this result for variable coefficients. So instead of having just the pure Laplace, I had a divergence form operator with variable coefficients. And in that case, we were still able to prove, if the coefficients were Lipschitz, that the minimizer had optimal regularity, C1 1/2. With respect to the free boundary that I told you is also something that we're very interested in. So let's remember that in this case, the free boundary lives in a dimension less, and it's the boundary of the set where u is equal to the obstacle phi. So it's actually very hard to study the geometry of the free boundary, significantly harder than the regularity of the minimizer itself. So because it is actually so difficult, what we do in free boundaries is we generally subdivide the free boundary in different parts where the function has different types of behavior, and then we say things about these different portions. And oftentimes we're not able to say something about all of the portions. So there are still open questions. A crucial ingredient that I would like to tell you all about, both to prove regularity of the minimizer U and also to study the free boundary, is Almgren's monotonicity formula. This is a beautiful result. So this was first proved by Almgren in 79 in a different context. So he was not working with free boundaries. This was not a thing. He had a function that was an honest harmonic function. So this function had Laplacian of u equals 0, let's say in a unit ball. And then he proved that if you think about a function of one variable, and the variable is r, playing the role of a radius of a ball or sphere, and you define this frequency n, so this is equal to, you look at the Dirichlet energy, the integral of the gradient squared over a ball of radius r, let's say centered at 0, everything for now. You multiply this by r, and you divide by what we call a height function. So that's the integral of u squared over the sphere of radius r, centered at 0. Then as a function of the radius r, this is monotonic, which is super incredible. And you can do this by taking a derivative of this function and showing that it is greater or equal to 0, using the fact that we have a harmonic function. You're going to have to integrate by parts. And then we can also prove, which is another very important thing for free boundaries, that this function n is constant, equal to, let's say, kappa, if and only if the function u is homogeneous of degree kappa, which means u of rx is equal to r to the kappa u of x. So this is something that is pretty incredible and has very deep applications when studying the geometry of the free boundary. Let me tell you a little bit about this. So how do we use Almgren's frequency formula? So in the case of the free boundary, okay, in the thin obstacle problem, we were able to prove a generalized version of this frequency formula because this was in principle just proved for harmonic functions. But if we have a solution of the Signorini problem, it's not harmonic because it's not harmonic across. But you can still prove a version of this formula. And then if you have a function that is monotonic and it is greater or equal to 0, the function n, the frequency, it has to have a limit as the radii goes to 0. So in the case of the Signorini problem, you can prove that this limit at 0 is greater or equal to 3/2. And this number 3/2 is crucial to prove the regularity of the function. Let's remember that we wanted to prove the function was of class C1 1/2, which morally means that I want to show that the function is less than or equal than a constant x to the 3/2. And this 3/2 right here comes from the Almgren monotonicity formula, which is beautiful. We also use this frequency function from Almgren, generalized to the context of the Signorini problem, to subdivide the free boundary. For example, you can prove even more. So not only is this limit as the radii goes to 0 greater or equal to 3/2, but it's also either 3/2 or greater or equal to 2. So that's super insanely cool. And the part of the free boundary in which the limit is equal to 3/2 turns out to be very special. And I know this is funky, we call it regular, even though it's very special. And it's regular because for those points, we can show that close to those points, the free boundary is the graph of a C-infinity function. So that's why regular. And then you have to look at the other points in which the frequency is 2 or higher. And how do we do this? So what we do is we pick a point on the free boundary, and the idea is you want to zoom in. Think of your phone when you zoom in. That's exactly what we're doing. So we rescale our function, and we want to let this process go to the limit, right? We're going to take a limit, and we want to see in the limit, do we get a solution of our problem that is maybe better, has more information about it? And in general, it will have more information because it will be homogeneous. Again, related to the fact that Almgren's theorem told us that if the frequency was constant, the function was homogeneous. So these are connected. So let me mention that in 2008, once again, Caffarelli, Salsa, and Silvestri, once thinking about the Laplacian case, they were able to prove that the set of points on the free boundary for which the frequency is 3/2, this is actually locally a C1 gamma regular surface. That means if you pick a point there, then close to that point, the free boundary is the graph of a function that is C1 alpha, assuming the manifold is flat and the obstacle is of class C21. And then we generalized this result in 2016, assuming that we don't have the Laplacian operator, but rather a divergence form operator. So you have divergence of A gradient U, and A we assumed was locally Lipschitz, and we were able to prove that this part of the free boundary, once again, is a C1 alpha regular surface. And to prove that, we used some other monotonicity formula that is very similar or very connected to Almgren's, and something called an epiperimetric inequality. In the same year, Koch, Rulin, and Shi were also able to prove that this part of the free boundary is regular using Carleman estimates. So just to see how a lot of different people are approaching this problem also in different ways. And then, folks, let me tell you about another portion of the free boundary. So we have the regular part where the frequency is 3/2. Then we have the part of the free boundary in which the frequency, which is the limit of the function n, as the radii goes to 0, is an even number. And that is called the singular set. But notice that we have the regular, that's the 3/2 frequency. We have the even frequencies, those are the singular. And then we have the other ones. And we know very little about the other points, by the way. So still open questions there. The singular set, if it looks funky to you to define it like, well, it's the points on the free boundary where the frequency is an even number, you can actually see it in a different way. So this is the collection of points on the free boundary for which the coincidence set, which is the set where you're equal to the obstacle, has vanishing n-1 dimensional Hausdorff density. So this tells us, in a sense, how big this set can be. So a point is singular if and only if, when you look at the coincidence set, and then you intersect it with a very little thin ball centered at that point with radius r, you look at the measure of that, and you divide by the measure of that thin ball. As the radius of these balls goes to 0, if that goes to 0, you have yourself a singular point. Okay. So here I will say just a few things, and I'm going to assume that the obstacle is 0 for this part of the discussion, so I don't lie too much. So in 2009, Garofalo and Petrosian, assuming that we were talking about the Laplacian operator, so minimizing the gradient of U squared, in this case, they were able to prove that for the Signorini problem, the set of singular points was contained in a countable union of C1 manifolds of dimensions 0 all the way to n-2. So this is a stratification result of the singular set. And we were able to generalize that, assuming that we were not minimizing the Dirichlet energy, but a generalization of that. So we were generalizing it to minimize the integral of A gradient U. So the operator that comes from this is a divergence form operator, assuming that the coefficients are locally Lipschitz. And we were able to also prove this stratification result. And we did this by proving some other monotonicity formulas connected to Almgren's as well. So that is what I wanted to tell you about today. Thank you so much. I'm excited to chat with you more about this. There are a lot of very interesting open problems in free boundaries, and these are just some examples of free boundary problems to motivate. Thank you so much.